All right, if we're done discussing cookies, we'll get started. Just before I turn it over to Andre to introduce today's speaker for Nano-Tech, just a word about the next meeting. We'll be meeting in 2 weeks on March 7th, and we'll also have a speaker from outside Georgia Tech, a visitor to Georgia Tech, Dr. Shalu Rakija from University of Illinois Urbana-Champaign Department of Electrical and Computer Engineering. And with that, I will turn it over to Andre to introduce today's speaker.
All right, great. Thank you very much. You guys can come closer. Don't hide there from far away. And this, oh, yeah, there's mic. Yes, that's now you can hear me. See? Come closer. I see familiar faces. I'm glad you came. Well, I'll be fairly brief. I want to give all of the time to our distinguished speaker today to actually discuss the exciting science of ion soft landing. But still, I want to introduce Dr. Grant Johnson, who's visiting us today from PNNL, Pacific Northwest National Lab. And we were just looking at establishing a timeline. So apparently he's been there since 2010. He received his undergraduate education from Syracuse University and then PhD at Penn State. And after this, it followed distinguished Linus Pauling, Nobel laureate, right? Yeah, Nobel laureate, twice Nobel laureate, distinguished postdoctoral fellowship at PNNL, working with Julia Laskin. I think that's probably where the first encounter and passion with ion soft landing started, along with multiple other things. Grant has been really a leader in this whole new discipline of ability to place in a very gentle, soft manner atoms on the surfaces to create a very unique properties for a variety of application. And most recently, I think the focus is at the separation science. I'm going to let Grant start with his talk, and I see more people showing up. Hopefully they will just quietly walk in. Grant, it's all yours. I'm gonna turn these things off, right? I'll let David turn this off.
Okay.
Wait, put off. Right?
Well, thank you, Andre. Assume you guys can hear me okay. So yeah, my name is Grant Johnson. I'm a scientist and team lead at Pacific Northwest National Lab. And I'd like to tell you today about a technique that we've been developing there over the last 15 years or so, known as ion soft landing. This is a way basically to prepare extremely well-defined surfaces containing species of known composition and charge. So to give you an idea, we have a cover from a recent Unconventional Chemie article here, and this shows you the various metal oxides, clusters, and peptide species that we've worked with over the last 15 years or so. So when you start thinking of ion surface interactions, these can span a broad range of energies, as shown on the left-hand side here. You can have relatively low energy species or processes, such as fizzy and chemisorption, elastic scattering in this so-called thermal range. You can have sort of intermediate energy processes, of which soft landing is one, in this hyperthermal range, up to about 100 electron volts collision energy. And then in the higher energy range, you have some of the processes that are used in surface analytical techniques, such as sputtering and surface-induced dissociation. So for the purpose of today's talk, I'll be focusing mostly on lower energy processes in this low hyperthermal energy range of ion soft landing. I'll be giving a talk in 3 parts, basically, focusing on the 3 species shown on the right-hand side. The first will be polyoxometalates, which are metal oxide clusters containing 12 metal atoms and 40 oxygen atoms. These can be molybdenum, tungsten, or vanadium. I'll then present some results on ionic liquid clusters, which we use for separation of metal ions. And if there's time, I'll conclude with an overview of some of the work we've done on larger nanoparticles in the 2 to 15 nanometer diameter range. So let's start with polyoxometalates. So this idea of modifying materials using ion beams is not new. In fact, it's the original way that they refined uranium during the Manhattan Project to produce the atomic bombs. And here, basically, you had an atomic source, you had an electromagnetic field that deflected different isotopes to different extents, and this allowed you to collect enriched uranium-235. These were very large devices, as you can see here, and because the currents were so low, they set these up in large racetracks where they were run in parallel, and they had sort of large groups of women that were sitting there tuning the ion current and making sure that the production targets were met. And this is all because the men were off fighting in World War II. So the first system I'd like to tell you about today is polyoxometalates, which are these metal oxide species shown on the left-hand side. They can span a range of sizes all the way from 0.5 nanometer up to about 5 nanometers or even larger in some cases. These are produced in solution using standard sort of techniques, combining these reagents. This results in the formation of a seed, which you can expand the coordination shell of to give you larger clusters such as those shown here. Our interest in these at the Department of Energy stems from the fact that they're highly redox active. This is a cyclic voltammogram showing the various redox states of this particular cluster shown here. And you can see that these species can accept and donate large amounts of electrons, which makes them potentially interesting for energy storage applications. So we've done quite a bit of fundamental work in this area, studying their interactions with well-defined interfaces. Anyone that's interested can refer to these articles from a few years ago. Today, I'll be talking about these species in the context of energy storage. They have been called electron sponges or molecular batteries. Previous work showed that you can take these species and immobilize them on something like a carbon nanotube electrode. If you take an electron micrograph of such a material, you see something like this, where your carbon nanotubes are coated with the polyoxometalates. What's particularly interesting, though, is that these species can be cycled between different charge states, all the way from 3- up to 27-. So 24 electrons can be packed into something that's around 0.5 nanometer in size. So clearly, this is quite a lot of energy density that's useful for storage in supercapacitors. Our approach to preparing these materials on interfaces involves ion soft landing using the instrument shown schematically here. We typically start with solution, with species in solution. We introduce those to the gas phase using electrospray ionization. And then these are transmitted into vacuum through an inlet, which removes the solvent and converts a droplet basically into a bare gas phase ion. We have two high throughput electrodynamic ion funnels which transmit those desolvated ions into vacuum. And then we have a quadrupole mass filter which we use to pick out one species of interest from that broader distribution of ions, which is then deposited onto a surface through a series of lenses. Some of the species that I've worked with in my time at PNNL are shown here: gold clusters, organometallics, the polyoxometalates I'll be talking about today, and then also proteins. One thing that's notable about this instrument is this new double ion funnel design, which has allowed us to substantially increase the ion current that we deliver to the surfaces. This is important because it directly affects how long it takes us to create a new material. This instrument is described in a recent article in Analyst, and to give you an idea of what it looks like in the laboratory, I have an image on the right-hand side there. So, as I mentioned, we were interested in the electrochemical properties of these clusters, so we needed a way to measure their redox properties and to do so in vacuum following deposition from the gas phase. So my colleague Venki Prabhakaran, who is an electrochemist, came up with a really clever idea of taking a screen-printed electrode, shown here, coating it with an ionic liquid membrane, which looks something like this in the electron microscope. And in so doing, this basically creates a conductive layer on your electrode into which you can then soft land your polyoxometalate ions. You can then attach a potentiostat and perform cyclic voltammetry measurements as shown on the right-hand side. So this is novel because up to this point, cyclic voltammetry had not been performed in the vacuum environment of a mass spectrometer before. And this is made possible by this membrane and the fact that ionic liquids have essentially no vapor pressure. Another notable thing about this work is the fact that we can generate fragment ions through gas phase collision-induced dissociation. This involves taking a parent ion, such as this molybdenum-12 species, accelerating it in the presence of a background gas and causing fragmentation to form the two constituent parts. Those can then be soft-landed, so you can study the electrochemical properties of something that you cannot produce in the solution phase using this approach. So what we did here is we prepared a supercapacitor device through this ion soft landing approach, and we did it two ways to try and understand the benefits of mass-selected ion deposition. So on the left-hand side here, you can see these clusters are deposited. They come down basically as discrete ions without any solvent and without any counterions. On the right-hand side, we did a deposition without mass selection just on the benchtop. And here you have counterions and solvent present. If you look at these charge-discharge curves, this basically represents how much energy these supercapacitors are able to store. And you can see here that the soft-landed device had a much higher charge storage potential than the devices prepared using drop casting or electrospray deposition. On the right-hand side, we have the cycling stability of these devices. And you can see basically as you discharge it and discharge it, species prepared conventional ways show a substantial decrease in their charge retention, right? So we're about 30% reduction there. Whereas those prepared by ion soft landing retain almost 90% of their charge storage capacity, which is a clear advantage for energy storage. So why is this? Well, to understand that, we needed some sort of spatially resolved characterization technique. So we started at relatively low spatial resolution using scanning electron microscopy, as shown on the left. On the top, I have the results for deposition, where you have full droplets reaching the surface. And on the bottom, I have the results for mass-selected ions, where only the discrete polyoxometalate reaches the surface. And you'll note here there's this sort of filamentaceous matter in these blue circles here, which is not present when you do deposition of the mass-selected ion. At even higher resolution, now at about 2 nanometers, you can see in the STEM imaging that electrospray gives you much larger aggregates, whereas mass-selected soft landing in vacuum gives you discrete clusters in intimate contact with the surface. And in fact, if you rotate this known structure of these clusters, you can actually line it up and identify species as being intact polyoxometalates. So we think, in a cartoon sense, we've produced something that sort of looks like that on the right-hand side. So that was an interesting sort of fundamental observation, but we wanted to move beyond that and see what could we do in terms of doping of these atoms to improve their performance. The idea here is that pure molybdenum containing clusters tend to be more reactive, while those that are tungsten containing tend to be more stable. And we believe that if we found the right mixture of both atoms in these clusters, we should be able to optimize and balance those two competing concepts. So you can combine these two species in solution, and when you do, you get a distribution of mixed clusters containing both molybdenum and tungsten atoms. And that's what's shown on the right-hand side here. And now with soft landing, we can go through and we can pick out each one of those species, isolate it from everything else, and deposit it and build a supercapacitor device just out of that. And this basically allows us to look with atom by atom precision how metal doping affects the performance of a supercapacitor. So the results for energy storage are shown on the right-hand side, and the cyclic voltammogram is shown on the left. You can note there's quite different redox behavior depending on substitution of molybdenum atoms for tungsten. What's most surprising, though, is when you look at the specific capacitance, substitution of just a single molybdenum atom results in a drastically increased specific capacitance. I naively thought that this would be sort of a linear approach that or effect that you would see go up sequentially with the number of doped molybdenum atoms, but it's only really one that's necessary to give you almost the highest performance possible. So one of the nice things about a technique like ion soft landing is the material that you've made is extremely well defined. It's not a mixture of a bunch of random things that you don't know what they are. And because of that, it's easier to characterize experimentally, but also easier to model theoretically. And we were very fortunate to collaborate with Joseph Poblet, who's been working on these systems for years. And he went through and used density functional theory to calculate all of the different ground state geometries of these various ions, which are shown on the left. And then he calculated the electronic structure, specifically the lowest unoccupied molecular orbital, as shown on the right-hand side. And what the LUMO is basically is the orbital into which the electron goes when you charge this capacitor, right? And you can see that substitution of a single molybdenum atom results in localization of that orbital almost entirely on the molybdenum site. So we believe it's that single substitution and that localization of this orbital that's responsible for that increase in the performance that we see with single substitution of a molybdenum atom. In addition to energy storage, you can also use polyoxometalates potentially as molecular qubits for quantum computing applications. So the idea here is you would dope the cluster with something like vanadium, which contains a spin unpaired electron, and then you would be able to create an array of these on a surface that would serve as a quantum gate. The issue is that it's not really understood how the oxide structure around those sites affects their decoherence rates, and it's also not understood how interactions between individual clusters and the surface affect their performance. So on the right-hand side here, you can see the various things that affect spin decoherence. The one that we're concerned with today is this one, number 4, the spin lattice relaxation. And this is basically how the vibrational modes of that cluster that we're using as a qubit will couple to the surface that's supporting it underneath. So first thing we needed to do was make one of these spin-doped polyoxometalates, as shown on the left-hand side. And that's fairly easy to do through substitution in solution. And then we needed a surface where we could change the functionality that that cluster interacts with to see what effect that has on the vibrational properties. And for that, we have picked self-assembled monolayers. These are easy to make on gold. They have well-defined structure and functionality, and you can change the terminal functionality from, say, methyl to CF3 to carboxylic acid. And this gives you a way to look at how specific interactions with those deposited clusters affect their vibrational modes. So before I get into that, one thing that bears mentioning is that these clusters are inherently 3- species. And when we deposit them on these self-assembled monolayers, we find from infrared spectroscopy that they actually retain their 3- charge on the surface. Well, how do we know that? Well, we can calculate the vibrational modes of these clusters using density functional theory. And in particular, the metal-oxygen terminal bands, which basically are this one here, have a characteristic vibration here, this wave number, which shifts dramatically towards higher wave number as the charge of the cluster decreases, right? That's what we calculated. On the surface, though, when we make the measurement, we find that those bands are not shifted. They stay essentially in the same place. So this is pretty good evidence that these clusters remain as 3- species on the surface. So we have a team that worked on this. First, we had, as I said, to produce this vanadium-doped cluster, which is done in solution and looks something like this. Once you produce this solution, if you look at it with analytical mass spectrometry, you can see a distribution of things in solution containing various numbers of tungsten and vanadium atoms. So if we were to just take a droplet of this, all of this material would be on our surface, right? And it would be very hard to correlate the activity that we see with any given species. So before we proceeded with soft landing, we wanted to understand the electronic structure of this doped cluster in the gas phase, which we did using anion photoelectron spectrometry. This involves taking one of these mass-selected ions, interrogating it with a laser, and measuring the kinetic energy with which that electron is released. And this gives you some insight into the electronic structure as shown on the left-hand side. As you can see, this 4- species has much lower detachment energy than the comparable species containing molybdenum or tungsten. In solution, what we can do is soft land that species onto an electrode surface, which we can then assemble into an electrochemical cell as shown here. And we can make the same sort of cyclic voltammetry measurements as I showed you before, but now we have the purple species, which contains a single vanadium atom. And you can see the dramatic effect on the redox properties of that cluster as a result of a single vanadium substitution. So when you're working with molecular qubits, one issue, of course, is how they interact with the surface and interact with each other, and underlying that is their charge. So we have here some results following soft landing of these qubits onto different self-assembled monolayers that were obtained using atomic force microscopy. This is a spatially resolved technique which allows you to basically interrogate the surface with near nanometer spatial resolution. And in this case, we can actually measure the height features, and we can also measure electronic properties such as the work function or the energy required to remove an electron from one of these deposited layers. And what you can see on the top is before deposition, these clusters have very similar work function, but after deposition, there's a split basically in the properties of these two layers. And we believe this is because more charge is retained on the fluorinated monolayer. So you have greater Coulombic repulsion, which makes that electron easier to remove than on the comparable other surface. What we were most interested, though, with respect to qubits is how the vibrational modes change, because this tells you how the energy couples from the cluster to the surface and what effect that has on the decoherence rates. So to extract that information, we used infrared spectroscopy in a reflection absorption geometry as shown here. Again, the cluster has a structure something like this, where you have characteristic vibrational bands corresponding to terminal and bridging bonds. And the infrared results here are for the same vanadium-doped cluster soft landed onto 3 different monolayers, so CF3, CH3, and COH terminated. And what I'll draw your attention to are the shifts in the vibrational bands of this terminal oxygen group. You can see here is quite pronounced on the carboxylic acid terminated monolayer. And this is also manifest as well in the bridging oxygen bands shown here and here. So what we learned from this basically is that the methyl and CF3 terminated layers, they have some effect, although small, on the vibrational modes, whereas the carboxylic acid terminated layer substantially distorts those terminal tungsten oxygen bands. So this would potentially give a pathway basically for loss of coherence through vibrational coupling to the surface. One thing that's also nice about this soft landing technique is it allows you to prepare a surface with varying coverage. And this is because your beam has a Gaussian intensity profile. So the center of the beam is most intense, and it falls off in a bell-shaped curve toward the edges. So when you integrate that over a deposited spot, you end up with something that's most high coverage at the center and lowest coverage towards the outside. So why is that important? Well, you can take a spatially resolved probe where you go in and basically measure spectra at all various points across this spot. And in so doing, you can get the infrared spectra basically as a function of surface coverage in one deposition. You don't have to go through and do 10 different depositions at 10 different coverages, right? Which is obviously a substantial advantage. So in fact, we did that with nano-IR, which is a spatially localized infrared spectroscopy. And we were able to show how these bands shift as a function of coverage. And the data is shown in a different form on the right-hand side. And you'll notice that it's most intense around 1020 at the edges and is most intense around 900 at the center. So what's the interpretation for that? Well, at the edges, you basically have clusters that are in contact with the surface that are far away from each other. They don't really interact or see each other. As you move closer to the center, these clusters become much closer at higher coverage. They begin to interact. And at the very center, it's possible they may even be piled up on top of each other. So instead of having an interaction with just the monolayer, you may have clusters interacting with clusters that previously arrived on the surface. Here's our results we obtained from tip-enhanced Raman spectroscopy. And the idea here was to try to understand the heterogeneity that occurs on surfaces even under these well-defined conditions where you have a monolayer with mass-selected ions soft-landed. Now, when we initially tried to obtain these spectra, it failed because we did not have significant enough enhancement. So my colleague, Patrick El-Khoury, came up with this idea of creating arrays of defects on surfaces using an AFM tip, where you just push the tip into the surface. And this gives you high aspect ratio features which enhance the electric field and also the Raman spectra that you see resulting from it. So here is a close-up of a single defect and spectra taken at 3 different points. And you can see that even on a surface that's prepared under such well-defined conditions, you still have substantial differences in the spectra, meaning the interaction with the surface is highly dependent on whether there are local defects or changes in the curvature off that self-assembled monolayer. So that's the first part of my presentation. I hope I showed you that we can use soft landing as a way to prepare really well-defined molecules on surfaces, particularly charge and stoichiometry-dependent redox properties of these palms. We can optimize properties by atom metal substitution, which is very challenging to do in the solution phase. And that substrate and intermolecular interactions do indeed influence the vibrational properties of magnetic palms, which means this will have to be taken into account as we move forward and try to create molecular qubits and quantum computers. For the second part of my presentation today, I'm going to talk about ionic liquids, which my group is interested in for separating metal ions from solution. So most people are probably familiar with the concept of electroplating. You can take a solution of a metal ion, you can put an electrode in solution and bias it. This will cause migration to the electrode. And if the potential is right, you will also reduce that cation to form a metallic deposit, right? So that's sort of emblematic of what's going on here. It turns out that the transport and also the interactions with that double layer depend quite dramatically on the local environment at the electrode. So we've been playing around with ways to tune that local environment to try to reduce the energy barriers to desolvation and adsorption. And one way we've been doing that is by introducing ionic liquids to create hydrophobic domains at electrodes that help to strip that solvation shell from surrounding metal cations. So where we started was in the gas phase. You can take a mixture of ionic liquids in methanol and you can electrospray them to get a distribution of ions. When you do that, in anion mode, you see something that looks like this, where you have a distribution of clusters containing different numbers of the imidazolium cations and chloride anions that make up these ionic liquids. You also see doubly charged species that are mass degenerate with the singly charged species. So it's extremely important to have the mass resolution to be able to distinguish the two and know that you have a pure species when you do the deposition. We can also select these and do collision-induced dissociation, fragmenting them in effect, and generating product ions. And this gives you an insight into what products are formed and also how much energy is required to fragment these. So it's representative of their relative stability. Because these species are well-defined and contain well-defined numbers of cations and anions, we can again rely on theory to predict their structures. These are density functional theory calculations on the left-hand side. As I said, we can go through with the mass spectrometer and measure their relative stability as a function of size. So these numbers in the brackets here are just the numbers of EM, IM, and CL groups in each cluster. And you can see that the amount of energy required to fragment these drops off precipitously with increasing size. So the bigger they are, the less stable they are towards fragmentation. And this is actually borne out as well in the calculations where they calculated the energy required to remove a neutral unit from each of these clusters, and we see the same sort of decay, which supports the experimental results. The electronic structure of these is also very important because we're planning to immobilize them on electrodes and use them to try and remove solvation shells from ions. So we obtain photoelectron spectra of these clusters as shown on the left-hand side here in collaboration with Zhubin Wang. This gives us an idea basically of the energy required to remove an electron as a function of the size of the clusters. We were also able to calculate the electrostatic potential for each of these clusters, which gives you an idea basically of how the charge is separated on these surfaces and where a cation might selectively interact with these clusters on an electrode. On the right-hand side are some of the results showing the change in charge when you remove an anion, and then the agreement between what was calculated and what was measured experimentally, which is, in this case, reasonably good. So, in the case of separations, one of the key things we're concerned with is what's known as the charge transfer resistance, right? We have an electrode, we have ions that are coming to that electrode, and this is one of the key parameters that determines the efficiency of that process. So a technique we can use to measure that is known as electrochemical impedance spectroscopy. We use an input AC signal, and we measure essentially a phase-shifted AC signal as our signal or data points. In this case, we used iron ferrocyanide as a model system, and this allowed us to determine the charge transfer resistance both before, on the left-hand side, and after repeated cycling of these electrodes, which contain these ionic liquid clusters. And what I'll draw your attention to is how much reduced this charge transfer resistance is in the case where we soft landed these ionic liquid clusters. So we believe that this is a promising way to help increase the efficiency of ion separation from solution. And we think that we can actually further tune this behavior using the size of the ions, so 1, 2, 3, 4, 5, 6, and we'll be proceeding with that work in the future. So to summarize the section on ionic liquids, these have size and stoichiometry dependent properties that we can measure, both their stability and electronic structure. We find that the stability towards dissociation decreases with size, and the electron detachment energies increase with increasing size. And that soft-landed ions can be used to form hydrophobic domains on electrodes that reduce the charge transfer resistance involved in separating ions electrochemically. The last portion of my talk will focus on larger nanoparticles, particularly platinum, ruthenium, and vanadium. The interest in these stems from their use in catalysts, specifically oxygen reduction catalysts that are used in fuel cells. So if you think of a fuel cell stack, something like this, one of the rate-limiting steps is the reduction potential involved in this particular reaction. People for years have been using platinum as a way to promote this reaction and make it more efficient. The problem, of course, is that platinum is very expensive and rare. So we'd like to find a way to achieve the same result, hopefully using something that's much more available and less expensive. So on the right-hand side, I have some results from the literature where theoreticians have gone in and sort of calculated various arrangements of atoms that would give you the ideal oxygen reduction potential for this important process. And on the top, you can see they think 2 layers of platinum on ruthenium is sort of ideal, and then down here they think in this core shell species that something with this stoichiometry would give you sort of the ideal reduction potential. And I mean, that's very helpful, but the issue is how do you make these things, right? There's not really a clear way to do that in solution because metals have different reduction potentials, and when you reduce them, you end up with a clump of one metal stuck to a clump of another in a lot of cases, right? So we thought we had maybe a unique way to try and address this problem, which is using the device shown here. It's essentially a different type of soft landing device. Here, though, instead of using electrospray ionization, we're actually growing nanoparticles in vacuum using a process known as magnetron sputtering and gas aggregation. So you have Metal targets located here, you flow in argon gas. This creates argon cations, which sputter the surface and create a metal vapor. That vapor is cooled through collisions with the wall. This causes nucleation and growth of clusters in a 2 to 15 nanometer size range. One thing that's unique about this device is that instead of one single target, you actually have 3, and you can control the power applied to each of these sputtering targets independently, which means, at least in theory, you can control the mole fraction of each metal that you incorporate into the nanoparticles. So because we generate a distribution of charges, cations, anions, and neutrals, we normally work with the neutrals, so those are extracted. We can use a mass filter to select a particular size range we're interested in, and then again, we can focus and deposit these materials at controlled energy. And this gives you a way basically to make a model catalyst material for oxygen reduction. So to give you an idea of what these things look like, I have some AFM results shown here in the middle. On the top, you can see sort of what copper nanoparticles look like at relatively low coverage on graphite surface. One thing that's interesting about graphite is it has this periodic stepped structure. So you end up at low coverage, basically. What happens is the ions go down stochastically, they sample the whole surface, and then they find that step edge where they get stuck, right? And then they form these extended chains. And that's what you see here. So if you run the AFM tip along here, you can see the size of these is about the same, 11 nanometers. If you kick the coverage up by an order of magnitude, you see a much denser coverage, obviously, where those terraces are filled in, but the size focusing is more or less retained. Now, as I mentioned, one of the things we were interested in making was a core shell species where we can put a core of a metal, say like platinum, around something less precious. Here is some evidence that, in fact, yes, we can do that. So this is sort of what the process looks like, right? You have metal vapors combining. And when you're done, you end up with something like this in the stem, where the Z contrast is higher in the shell than it is in the core. And that sort of indicated that the platinum might be in the shell. But of course, you have that issue of greater thickness when you look along the side, right? So we wanted to be sure, and we went in and did electron energy loss spectroscopy. And this basically allowed us to confirm that, yes, the platinum is in the shell, whereas the vanadium is located primarily in the core. So we think we generated basically something like this, right, that theoreticians are sort of interested in. So to test the catalytic activity, again, we can combine this into an electrochemical cell. Our surface basically goes here. There's a small volume of electrolyte trapped above it. We purge that alternatively with argon and oxygen, depending on whether we're making a background or a reduction measurement. And then we obtain the CV, and the critical value is the position of this voltage here, right, this curve. And we can basically make things that have comparable reduction potentials to precious metals, but contain a much lower loading of those metals. So to summarize this section, there are a number of advantages to this gas aggregation and magnetron sputtering approach to synthesizing nanoparticles. The first is that they're bare nanoparticles. There's no ligands, solvent, or contaminants. And removing these things is typically a huge problem when you're doing research, particularly for catalysis, where you need that active surface site. We can make novel core shell morphologies and alloys that you cannot easily make in solution, including some of the structures shown down here. And then when you combine that with ion soft landing, you can control the size, the composition, and coverage. You can vary the energy across a range from soft landing to pinning to actually implanting these materials down inside of the surface. And of course, because they're ions, you can focus and steer them, right? So you can do things like create ordered columns and things like that using masking techniques. So this brings me next to some work we've been doing in collaboration with Andre. So a few years ago, his group developed this device which basically improves desolvation for analytical mass spectrometers. And we realized sort of after talking about it that there might also be applications in sort of material production and ion deposition. So we made some sort of subtle modifications to it. I think Andre's original device had a single electrospray emitter. We sort of brought in 3 additional emitters to increase the amount of ion current that we could produce. And then we basically increase the gas pressure at which we run this, used heated gas. And the idea of this device is it creates a vortical flow of gas which converges right at those electrospray emitters. So as you're producing your sort of charged droplets of whatever you want to deposit, you have this high density of highly agitated gas that comes in there and basically strips any solvent from around those ions. The pressure then drives those out into the laboratory environment. We have a pusher plate which turns them 90 degrees and a lens which gives us some focusing. And then these are deposited on substrates. The nice thing here is any neutral material will not be turned by that pusher plate, so it goes off into space and is disregarded. And only the anions that we're interested in actually make it to the surface. So it looks something like this in the lab. You can see basically what the surface sits in this holder here. Here's the pusher plate, and then here's that vortical flow generator down here. So the idea with this was to see if we could get similar to results to what we get with mass-selected ion deposition in vacuum using a much more simple and cheaper device on the laboratory benchtop, right? So here we combined the same device produced using both of those techniques. And this, in this case, was a supercapacitor. And again, you can see the charge-discharge curves here. And you'll note that ambient soft landing using this device gives you very similar performance to vacuum-based soft landing. I mean, it's probably within sort of the error, right? And in fact, the specific capacitance as well is very much similar. So we wanted to see at a molecular level, is the dispersion of these materials on the surface the same? Is it different? What is responsible for this activity? In the case of vacuum soft-landed polyoxometalates, you see this sort of spidery distribution of ions on the surface, and you can actually make out individual atoms comprising those clusters. In the benchtop soft landing, it's similar coverage. The morphology is a little bit different overall, right? You don't have these spidery distributions. You have more this sort of island with a higher density in the center and then going out. But nevertheless, when you go in and you look, even at the highest density, you can still see individual atoms corresponding to the molybdenum and tungsten that's present in those clusters. And this is very different to that large aggregated crystallite matter that I showed you earlier in the slides, right? That was like 5 nanometers in size. You're still seeing atomically resolved species here. Another area that we worked on recently was using the same technique and clusters to try to prepare a device that would basically harvest and store energy in the same device. So we called it a photoelectrochemical energy storage cell, but it looks something like this basically, where you have an indium tin oxide surface. We deposited polyoxometalates onto that using Andre's device. And then in between that, we had an ionic liquid layer and then a redox anode. And when you shine sunlight on this, a broad spectrum light, it does in fact generate current, and that's what's shown on the right-hand side here. So this is basically a plot of what the measured current looks like when the light is on and when it's off. And the red and black are a comparison between a device prepared using Andre's desolvation tool and then prepared using just drop casting from a liquid phase. And you can see how substantial the increase in current is for a similar loading of material, right? So we're quite excited about this. Another thing that was interesting about this material is these polyoxometalates are photochromic, meaning that when you shine light on them, they change color. So there's potential applications for this in things like smart windows, basically, that once they're irradiated, they turn opaque, so they stop light from entering and heating the building. On the left-hand side, you can see a drop cast version before and after irradiation. On the left, on the bottom, you can see one created with benchtop soft landing. And in this case, we didn't even need electron microscopy. We could really see the difference in morphology just using conventional optical microscope. And on the left, you can see there's this sort of more fine dispersion, right, of the soft-landed species, whereas the drop cast, again, form these large aggregates, where a lot of the material is essentially wasted in the center of the material that doesn't interact with the substrate. So this was recently featured on the cover of Chemical Communications. One area that we've gotten into very recently is this idea of preparing samples for electron microscopy. So cryo-electron microscopy won the Nobel Prize, I think, a year ago. And the reason why is it basically allows you to structurally resolve, protein complexes that are on the order of, a couple nanometers in size. I mean, it's really quite amazing. In order to do that, though, you have to have these proteins trapped in a liquid layer. And that liquid layer has to be amorphous and not crystalline. Otherwise, you get, scattering, which messes up the microscopy. So we were interested in could we just purify a protein complex and put it on a surface, and what would it look like in the TEM if we soft landed it? So we did that for apoferritin, which is shown on the right. These are two results from two different samples. You can see basically, yes, indeed, we can produce fairly high densities of these proteins. The objective in cryo-TEM is basically to cover the surface in a single layer of these things so that you can sample all possible orientations, then do a 3D reconstruction. So what you don't want is things preferentially oriented one way or clumped up on top of each other. So we think that this is a promising result and something that we're hoping to build on in the future. Where are we headed in the future? Well, one of the problems, not problems, but limitations of the technique up to this point is that you deposit one polarity of ions, right? So if it's a conductive surface, it's not a big deal. It discharges and you're fine. But if it's an insulating surface, you actually build up charge. And this can be enough to actually deflect your ion beam and stop your deposition. So we've been looking at ways to deposit both polarities of ions, positive and negative, simultaneously. And one way to do that clearly is to have a cation and anion beam coming in at the same time to a substrate, maybe even with some background gas to build up a sort of matrix around it. The problem with this approach is that it doubles the requirements for the instrumentation and pumping and electronics, so it's a very costly proposition to do that. What's a little bit more clever was actually worked out by my former advisor, Julia Laskin, who's a professor at Purdue University. And here what they did is they took two electrosprays, one positive and one negative, and then they developed a set of electronics basically that allow rapid switching of the whole mass spectrometer from one polarity to another. So you can transmit alternatively cations for a few milliseconds and then anions for a few milliseconds. And you can change the length of each of those pulses. You can change the length of time in between them to get essentially something that's tunable in this sort of space shown here. And this was done with Gordon Anderson, who runs a custom electronics company for mass spectrometry. So we're going to be copying that technology going forward, basically. And one of the ideas we have is actually to use that to try and build up a solid electrolyte interface at an electrode to try and model what goes on in batteries during the charging and discharging process. So at long last, that brings me to the end. I really appreciate you're listening to my presentation. I just acknowledge the funding organization, of course, which is Department of Energy, as I am at a national lab. I'd also like to just point out that PNNL just recently built a new building for physical sciences, shown here. Offices are over here and the labs are over here. And this is a great place to come and work on problems in the physical sciences. As I said, I've been there about 12 years, but we have large numbers of postdocs and we have people that come for shorter stays. So we're always willing and interested to host new people. So I'll stop there and I'll be happy to answer any questions. Thank you.
Questions?
I have a quick one, just right away. Grant, when you show just very basic on the fundamental of ion soft landing, both as compared to just electrospray deposition, electrospray delivered ions. So the basic fundamental difference between just sprayed material versus ion soft landed, obviously, and the energy of those ions, right, that lands on the surface. Mm-hmm. So how is that? So is that the reason why it is so important to do it in vacuum, where you have all of this staging with the electrostatic focusing, or how is that being achieved, the precise tuning of the energy of those ions?
I mean, I think the main issue is if a droplet of any size reaches the surface, then you have these drying effects. I mean, they seem almost unavoidable, right? So I think in the case of solutions where you can prepare, say, I mean, we can buy these polyoxometalates and the solution contains maybe one or two things, right? There it's easy to go ahead and do it without mass selection. But if you have a complex mixture, like I showed for the two metal containing, then in that case, I mean, you have to have the mass selection, right? I mean, there's no other way to exclude and have any certainty of what you have. Does that make sense? Yeah, okay.
Other questions?
So it's first of all, it's great talk. So, so if I see page 1 or 2, you show the TM image showing the core-shell nanoparticle. Page 1 or 2, but it looks like the shape looks like the cube shape. I was so surprised.
Oh, the vanadium ones? Yeah, hold on. Yeah.
So-
Yeah, this one?
Yeah, actually, it
I
looks like-
didn't talk specifically about that one. So that's, I think that's vanadium with copper around it, if I remember right. But we were really shocked by this too, and they were all pretty much cubic, which was
Yeah.
very strange. But you can see there's this sort of oxide shell or whatever around it that forms. So these were analyzed after exposure to air. So there's always a bit of oxide passivation.
Yeah, the reason I'm asking because nanoparticle society really trying to control the shape. For example, if you create nickel 111 or 100 and coating the platinum, that can improve further OR activity, something like that. So I just wondering, is there any possibility to control the shape using your method?
There is, but I would say it's almost entirely empirical at this point. You know, we see it happen. We don't really know why yet. So, yeah.
Kind of interesting. Yeah, so this shape control, in addition to selective chemistry,
Yeah.
it really will bring a whole new dimension then, perhaps even for selectivity of some chemical reactions. I think you'll have to go maybe not to the very high vacuum. Maybe you can utilize some hydrodynamic effects.
Yeah.
If you operate in the intermediate vacuum, so you can utilize kind of cross-sectional dependence as you drive those
Yeah,
ions.
so you're saying like a mobility separation? Yeah, you could do that. Yeah. I mean, one thing we've talked about is trying to put some kind of spectroscopy actually in that sputtering and aggregation region to understand, you know, is there some signature of these things that you could use to tune conditions? But no one gave us funding yet. So.
We can send it right in. These meetings.
Yeah, thank you. Fascinating work. Just to follow up on what Dr. Fedorov was asking about, sounds like the effective desolvation is critical for the soft landing, and I think that's kind of the idea behind the drill or vorticial flow, right? Have you looked at just assuming you have effective desolvation, the absolute velocity? I mean, does that matter, especially for something like proteins, or if you're trying to do that?
Yeah, it does. So I mean, I mean, there's part of the reason we work with the systems I've shown is because they're reasonably tough. So the polyoxometalates and also the nanoparticles, I mean, they're big enough they can take a pretty good collision. I mean, these things are going down at like 30 eV, something like that. You know, if you're going to do small, you know, 2 or 3 or 5 atom things, then you're going to have to slow them down to 1 or 2 eV to preserve them. One of the reasons we also use self-assembled monolayers is because they give you a little bit of cushioning as opposed to landing on just like a diamond surface or some, you know, rock hard thing. Yeah. Does that answer your question?
Yeah. Anything else? All right, of course. Andrei's going to have the last word.
That's why he needs to fly so far so I can ask all the questions, regardless when you collaborate.
Well, I might not be leaving right away.
Yeah, he's got to run away. I found this fascinating result between having this tungsten and molybdenum that you need to have only literally just one.
Yeah, it was very
atom of
surprising.
molybdenum. So obviously you have this explanation using density functional theory. I wonder if it can be extended generally to maybe some other material systems, because this is so important, right, for any rare element, highly expensive catalysis. Is that a general?
Well, I think people talk about, bringing the LUMO to the band level needed for transfer and things like this. I mean, we didn't really know what the band level or whatever was for the support, but I mean, I think in this case it was pretty clear it was moving it in the right direction, right? I think it's relevant. It sure is relevant, yeah. For energy storage, probably for catalysis, yeah. I mean, so for catalysis, they're always talking about what the D band level and how this, controls activation of molecules, right? So, yes.
Yeah, that's very fascinating.
All right. I think with that, we'll thank Grant one more time, and we'll see you in 2 weeks.